All right. We just have to talk about a couple of little specific situations. We're going to talk about a pendulum, and we're going to talk a little bit more about the mass on a spring. So, simple harmonic motion results for those two situations in particular. A pendulum at small angles, when you can assume the sine of theta is about equal to theta. If you do this on your calculator, you type in the sine of a really small angle in radians, and you say, oh, the sine of that angle is about equal to the angle. You have to be actually less than about 0.17 radians, so the sine of theta is about equal to theta, or it's, approximately 10 degrees. That's the situation when simple harmonic motion results for a pendulum at these small angles. Or once again, we've talked about a mass on a spring. We're going to talk a little bit more on that. Not a ton, but simple harmonic motion results in these two situations. Because you can picture like a mass in a spring oscillates back and forth, and a pendulum at small angles will kind of go back and forth. I can't do it with my finger, but you get the picture there. And remember, simple harmonic motion has to have two things occur. Number one, the acceleration or the force has to be proportional to the displacement. So if you have a big X, you're going to have a big A. If you have small x, you're going to have a small a. But I will say, it can't be x squared, it can't be x cubed, it's got to be x, and it's got to be a for simple harmonic motion. Number two, whatever the direction of displacement, if I pull it to the right, there's a negative on the acceleration or whatever, so it wants to accelerate back to the left. The acceleration has to be in the opposite direction of the displacement. So, number one, proportional, x and a have to be proportional. Number two, the acceleration is in the opposite direction. So let's look at our first situation here. We're going to talk about the pendulum. And you can picture like a pendulum, like you just pull it back from equilibrium right here, and I've like zoomed way in here. So it's just a small pullback right here, but it looks like it's a big angle, but we're just zoomed way in. And I'm just going to release it. And that pendulum will kind of go down to here, then back, change colors, and back to here, then on back. And you can graph that motion again. It started at a cosine wave. The cosine wave. It's just going to be the same thing we've been kind of talking about. But for simple harmonic motion to result and for it to hold true, the pendulum has to be at a small angle. It's called the small angle approximation when sine theta is equal to theta. And there's a special equation right here. I'm not going to derive it for you because I just want to keep it simple. If you want to know the period of this pendulum, so how long it takes to go down and then come back, it's 2 pi times the square root of the length of the pendulum divided by gravity, 9.81. All right? And a lot of people think, well, if I have a small angle or a big angle right here, there's no angle in this equation, so at small angles, the angle does not matter. And you can picture, oh, if I'm right here, it doesn't have as much PE, so it doesn't get going as fast over here. And if I pull it back farther, it has more PE, which means we get going faster there. But the big thing is this. There is no mass in the pendulum equation. There is no angle in the pendulum equation. The only thing that matters is the length of the pendulum and what planet you're on. Gravity, or maybe you go to the moon. It's not a different planet, but you're at the moon. Gravity is less. Well, if gravity is less, then all of a sudden the period divided by a small number, then the period of time will get bigger. All right, so just some notes about the period of a pendulum. If the length of the pendulum gets long, then the period of time goes up. It's a radical right here, so it's not like 1 to 1 because there's a radical over the L. If gravity gets bigger, so if G gets bigger, divided by a big number, the period of time gets smaller. So we have that going on. And one little thing, just the note, force is proportional to displacement once again. So that's the assumptions we're saying for simple harmonic motion. I'm not going to prove that in this video. And the acceleration is proportional to the displacement, but it's in the opposite direction. That's why there's a negative there. Remember, negative doesn't mean small. Negative means direction. So if you pull it to the right, acceleration's going to go. If you pull it to the right, it wants to accelerate back to the left. If you pull it to the left, it wants to accelerate back to the right. And one little mention, there's the graphing trick. If you squared both sides of this equation, and we're going to practice more of this, so that's t squared, and I squared this side, and then you're like, hey, I'm just going to rearrange a little bit. I'm going to pull the constants out front, put my variables by themselves. If you ever plotted t squared versus L right here, and you said, I'm going to plot t squared versus L, like I'm going to vary the length, that's my independent variable, my dependent variable is the time, in this case, length versus time squared, and you plotted that, you would get a graph like this, and you can put a line of best fit. If you took the slope of that, it'd be this constant out front. So you could say, hey, I know the slope of the line. It's called linearizing a function. So now when I plot L versus t squared, the slope right there, then you can set it equal to this, and you can solve for gravity. So there's lots of cool things. And t squared versus L, the slope gives you that, and you can solve for G. Just something to think about, okay? If you're just like, Laurent, I'm good with the period of a pendulum equation right now. I can find out how long it takes to go back and forth based on its length. Cool. That's a great place to be as well. All right? And then one last little thing. We talked about mass on a spring, and I didn't get a chance to give you the general formula for the period of time that it takes to go through one whole cycle. So if you ever know the mass at the end of the object right there, you know the spring constant, then you can use a similar formula. The reason I'm doing these in the same video is 2 pi squared of stuff, L over G, 2 pi squared of stuff, in this case the stuff's M over K. And well, if you have a very large mass, it's going to take longer time to go through a cycle, right? M gets big on this side, the T, the period of time it takes to do a cycle gets longer. If you have a big spring constant, so you're like, oh wow, dividing by a big number, that's going to make the period of time smaller. Well, that kind of makes sense because if this is a very rigid spring, like a car shock, you're like, oh, it went through a cycle very quickly because it had a high K, dividing by a big number makes a small period of time. And once again, you can pull the same graphing trick. T equals 2 pi squared m over k, square both sides, rearrange it, and you're like, oh, y equals mx plus b, there's no y-intercept. And you're like, hey, y goes with t squared, that'll go on your vertical axis. Then you'd have the slope would be the constant up front here, and then your independent variable, your mass, as you vary mass, that affects your time there, time squared technically. And so you could graph this, you could graph t squared versus mass, the slope would give you that, and then you could solve for k. There's just so many good little math and graphing tricks you could do. All right, so once again, if you're like, I don't want to think about graphs or math, or sorry, I don't want to think about math tricks to linearize functions, don't worry about it, but at least get down these functions. And on this one right here, they might say, oh, if I pull it back farther, does that affect the period of time of the mass in the spring? So if the amplitude is greater, well, check it out. There's not even an amplitude in this equation. So if you pull it back more, it has more potential energy, and it's going to accelerate more because you release it. So it turns out that, you know, within reason, because if you broke your spring, you pull it too far, then it's not going to accelerate backwards. But amplitude has no impact on your period of time for mass in a spring. That's a quick little video about the period equation for a pendulum, which is just a string. We're going to say it's a massless string with a mass on it, just like that. And it's really important, it does not depend on mass or angle for our small angle approximation. And the period of time for a mass on a spring, which does not depend on amplitude, like some people might think, it just depends on the mass of the object and the spring constant down below. So that's a real short video, and yeah, I hope that helped. And we're going to talk about one last little thing that's important, but it's not super important, it's just kind of a last idea just to put in your notes just in case. Thanks for watching.